Okay, this video is going to be our second video looking at amine chemistry. We're going to start off by looking at the Mannich reaction, so the alkylation of enols by iminium ions. While that sounds scary, those are all terms that you should be familiar with, right? Alkylation, we're going to be adding a new carbon-carbon bond of an enol. So we're looking at enolate ion or ketone, that's an enol, keto-enol tautomerism, and iminium ions, a double bonded nitrogen to a carbon, right? So here's an example of what you would see for a Mannich reaction. We start off with a ketone or an aldehyde. Usually you have a more reactive aldehyde. This is going to help in forming our iminium. In order to do that, we'll need an amine. And then you usually have alcohol solvent with HCl or some type of acid. And what your end product's going to be is a beta amino carbonyl product. So what this means is on the beta carbon from the carbonyl, there's an amino group. All right. So let's look at some examples. Here we have a aldehyde with formaldehyde and a primary amine. Our end product is going to have that carbon from the aldehyde as a new carbon-carbon bond coming from the alpha position of the aldehyde. So let's go through the mechanism. Our first step is going to be forming the iminium ion, which will involve two proton transfers. If you're not sure about this, you can refer back to an earlier video, but this is very similar to what we saw with our carboxylic acid derivatives, where we would replace that double bonded oxygen with a double bonded nitrogen. Has a positive charge, so it is a salt at this point. This is eventually what's going to be added to our other aldehyde or ketone. Enolization, that's going to be of our starting ketone or aldehyde. So we know enolization is going from a ketone to an enol, so a double bond with an alcohol. This is what allows that alpha position to act as a nucleophile. So the new carbon-carbon bond will be that bond acting as a nucleophile to the carbon position. Remember, the driving force for this, the first arrow you should draw is your electrons coming from your alcohol, pushing down, those electrons coming out onto the carbon, and then pushing your electrons finally onto your nitrogen. So you should be left with something like this. Your last step would just be a proton transfer, and then you're also going to need to end up using a base at some point to deprotonate your amine. The next mechanism we're going to talk about is the nitrisation of amines. This mechanism is a little hairy, but it's going to become really important in our next chapter with the benzene substituents. So our first step is going to be the generation of NO. So you'll see that our reagent is going to be on the left, NaNO2. We're going to use acid to help create water into a great leaving group. We can then use our resonance to create our nitrosyl ion. This is when our amine is going to act as a nucleophile, come out creating that N-nitrosammonium salt, with that first nitrogen being a quaternary nitrogen. It's not going to be very stable, and we sort of use that to our advantage. Why is that? If we use a little bit of acid, we can again remove another molecule of water, and then doing another proton transfer, we can create a diazohydroxide, which will then end up giving off the water, giving us our diazonium ion. This nitrogen compound is going to turn into a great leaving group, giving us a carbocation at our R, or our carbon source. So what you'll see is the nitrogen leaving, generating your R+, and then depending on what's around, you can have a wide variety of product mixtures. Secondary amines are actually a little bit more stable, so you can isolate those. Those don't have much synthetic use for this course. Why is this benzene ring our diazonium ion? It's going to eventually leave as a leaving group, and you can see that the carbocation is going to be stabilized throughout our benzene ring. So this is advantageous because once we turn our amine into our diazo group, we can then have that position be a source for new addition of a lot of different types of elements. If there's water around, you will see it become a phenol. So you can see here we've turned our amine into our diazo compound that can leave just with heat. That carbocation is not going to be stabilized within the ring. It's going to be very reactive and pick up anything it can find. This is an example of one of the reagents we'll talk about in chapter 22, or one of a similar reagent. I think your notes may use potassium iodide instead of hydrogen iodide, but you'll end up seeing that our NH2 or our amino group can turn into any number of halogens, in this case showing you as an iodine.